The universe is lying to you, not in the way a person lies, with motive and intent, in the way a wall lies, by being there, by blocking what's behind it, by making you forget that behind it is even a direction you could look. Right now, in a building in Santa Barbara, California, there's a machine hanging from the ceiling of a sealed chamber. It's cooled to 15 millikelvin. That's 15 thousandths of a degree above absolute zero. The cosmic microwave background radiation, the faint glow left over from the birth of the universe, the coldest thing that exists naturally anywhere in the observable cosmos, is nearly 200 times warmer than the inside of that machine. The machine has to be that cold, not because it needs the energy savings, not because the components are fragile the way glass is fragile. It has to be that cold, because if the temperature rises even slightly, the universe finds out what the machine is doing. And the moment the universe finds out, the machine stops working. Let me say that differently. The machine only functions when the universe isn't looking at it. In October of 2019, that machine, a quantum processor called Sycamore, built by Google's Quantum Artificial Intelligence Laboratory, completed a calculation in 200 seconds. The same calculation on the most powerful classical supercomputer on Earth at the time. A machine called Summit that fills a room the size of 2 basketball courts would have taken approximately 10,000 years. Not 10,000 hours, not 10,000 days, 10,000 years. A span of time longer than the gap between the first Sumerian clay tablet and the phone in your pocket, compressed into the time it takes to soft boil an egg. That number is interesting, but it's not the interesting part. The interesting part is what happens inside the machine during those 200 seconds, and why it has to be hidden from everything else in existence for those 200 seconds to count. Because the machine doesn't simply calculate faster. It does something that, if you follow the physics to its conclusion, shouldn't be possible inside a single universe. And the fact that it works anyway, the fact that it returns correct answers every time it runs, is what many physicists consider the first direct evidence that the universe you experience, the solid, stable, singular world you see when you open your eyes, isn't the whole story. It isn't even most of the story. It's the part of the story the universe has been letting you see, and the machine just caught it in the act. If you're new here, a like and subscribe would genuinely help this channel continue making content like this. Now, let's begin properly. You will see why a single particle stops being in 2 places the moment anything finds out about it. You'll meet the physicist who turned a philosophical argument into a number. You'll watch 50 years of experiments slam a door that Einstein spent his life trying to hold open. And you'll learn what happened in December 2024, when a machine did something that broke every engineering rule we've ever known. But first, let me tell you what's actually inside the machine. Not the sleek white exterior you've seen in photographs, not the cloud infrastructure or the cooling system. The thing at the center, the part, the whole machine exists to protect. It's a small chip, roughly the size of a postage stamp. It contains tiny loops of superconducting wire. Each loop is a qubit, and a qubit is not like anything else in computing. A normal computer bit is either 0 or 1, always. At every moment, it has a definite state. A 0 is a 0, a 1 is a 1. The entire history of computing is built on that simple fact. A qubit is different. Before it interacts with anything else, before the environment gets involved, a qubit exists in what physicists call a superposition. It isn't 0, it isn't 1, it's, in a very precise mathematical sense, a combination of both at the same time, weighted by probabilities that can be tuned and manipulated. I want you to picture that carefully, because it's easy to hear it and let it slide by. Imagine you flip a coin and catch it under your palm without looking. In ordinary life, the coin is either heads or tails. You just don't know which. That's a classical bit. It has a definite state. Your ignorance is your problem, not the coin's. A qubit isn't like that coin. A qubit, before measurement, doesn't have a definite state. The mathematics describes it as genuinely existing across multiple possibilities at once. The ambiguity isn't in your ignorance, it's in the thing itself, and that's exactly what makes quantum computers powerful. When you run a calculation on a qubit in superposition, you're, in a real sense, computing across multiple possibilities simultaneously. String together hundreds of entangled qubits, and the number of simultaneous states grows exponentially. 2 qubits, 4 states. 10 qubits, over 1,000. 300 qubits, more states than there are atoms in the observable universe. Sycamore had 53 of them. Now let's start with your hand. Hold it up if you like. Or just think about it. Your hand is made of atoms, roughly 7 octillion of them. Those atoms are made of electrons and nuclei. Those electrons are governed by quantum mechanics. They exist, at every moment, in quantum states described by wave functions. Mathematical objects that encode not just where the electron is, but where it could be, with what probability, and how those probabilities interfere with one another. In principle, your hand could exist in a quantum superposition. It could be here and there simultaneously, the way an electron passes through 2 slits at once in the most famous experiment in physics. The mathematics allows it. The equations don't contain any clause that says, except for objects larger than a bread box. You've never seen your hand in 2 places at once. You've never seen any object in 2 places at once. And the reason isn't that quantum mechanics stops applying at human scales. The reason is something else entirely. Something that took physicists until the 1970s to properly understand, and that most people have never heard clearly explained. The reason is that the universe won't stop touching your hand. Every photon of light that bounces off your skin carries away information about where your hand is. Every air molecule that bumps against your fingers records a tiny piece of data about your hand's position. Every thermal vibration in the table your hand rests on. Every infrared photon radiated by your body heat. Every interaction of any kind between your hand and anything else in the environment does the same thing. It carries away quantum information. It entangles your hand with the world around it. And the moment that information leaks out, the superposition is destroyed. This process has a name. It's called decoherence. And it isn't a minor technical detail. It's the reason you experience a classical world at all. A physicist named Wojciech Zurek, working at Los Alamos National Laboratory, spent decades making this precise. Building on earlier work by Heinz-Dieter Zär in the 1970s, Zurek showed that the classical world, the world of definite objects in definite positions with definite properties, isn't the fundamental layer of reality. It's what quantum reality looks like after decoherence has done its work. The process is unimaginably fast. For a grain of dust floating in ordinary air, decoherence happens in approximately 10 to the minus 31 seconds. That's a decimal point followed by 30 zeros and then a 1. It's faster than anything you've ever conceived of as fast. It's so fast that no instrument built by human hands could catch the grain of dust in superposition. By the time you could even begin to look, the superposition is already gone. Your hand, made of octillions of atoms, each one interacting with trillions of environmental particles every second, decoheres so quickly that the quantum superposition it could theoretically occupy has a lifetime measured in numbers so small they don't have names in ordinary language. I need you to sit with that for a moment. This is why the world looks solid. This is why the world looks definite. This is why you see one version of every object, one position for every chair, one outcome for every coin toss. Not because the world is classical at its foundation, because the environment is constantly, relentlessly, at every moment interacting with every quantum system around you and collapsing its superpositions before you could ever detect them. Zurek introduced a concept he called quantum Darwinism. The idea is that certain quantum states, the ones that survive environmental interaction, the ones that leave copies of themselves in the surrounding world, are the ones that become observable. They're selected by the environment, the way organisms are selected by evolution, not for fitness in the biological sense, but for stability in the informational sense. The states that get copied into the environment are the ones you see. The states that don't get copied decohere into invisibility. What you call objective reality is, in Zurich's framework, the small fraction of quantum information that the environment has selected, amplified, and broadcast into the world around you. It isn't everything that exists, it's everything that survived. Think about what that means. The classical world, the world of solid tables and definite positions and single outcomes, is a surface. It's what remains after the environment has stripped away everything else. And the everything else that was stripped away isn't nothing. It's the quantum superposition. The other branches, the other possibilities that were just as real, just as physical, just as present in the wave function until the environment reached in and scattered them into decoherence. You're not living in the whole of reality. You're living on its surface, the part that decoherence left visible. And right now, in laboratories around the world, engineers are building machines designed to do one thing: to hold a piece of that surface open, to prevent decoherence from doing its work, to keep a quantum system isolated from the universe long enough for the superposition to survive and do something useful before the environment notices. That's what a quantum computer is, not a faster calculator. A machine that holds open a crack in the surface of the classical world and computes in the space underneath. And the experiment that first revealed that crack is almost absurdly simple to describe. Take a beam of particles. Aim it at a barrier with two narrow slits. Behind the barrier, place a screen. Record where the particles land. If the particles behave like tiny bullets, you expect two clusters of marks on the screen, one behind each slit. Straightforward, intuitive. What particles should do? That's not what happens. What appears on the screen is an interference pattern, a series of alternating bright and dark bands, like ripples in a pond crossing each other. Bright where wave peaks meet wave peaks. Dark where peaks meet troughs. The pattern that only appears when waves interact. This was first observed with light, which was already understood to have wave-like properties. But then physicists ran the experiment with electrons. Individual electrons, fired one at a time, each one a single, discrete particle, arriving alone at the barrier with no other electron anywhere near it. And over thousands of individual impacts, the interference pattern appeared. Each electron, passing through the barrier alone, was somehow interfering with itself, as though it had traveled through both slits simultaneously, taken two paths at once, and the two paths had combined on the other side to produce the pattern. Your intuition wants to say, surely the electron went through one slit. We just don't know which. But that explanation doesn't work. If the electron went through one slit, there'd be no interference pattern. The interference is proof that both paths were taken simultaneously, in some physical, measurable sense. The ambiguity isn't in your knowledge. It's in the thing itself. That was strange enough. But then came the part that's kept physicists awake for 100 years. When scientists placed a detector at the slits, a device that recorded which slit each electron actually passed through, the interference pattern vanished. The electrons started behaving like particles again. Two clusters, one behind each slit, no interference, no wave behavior. The simple act of acquiring information about which path the electron took destroyed the superposition. Let me say that again because it's the thing that matters. When nobody was watching which slit the electron went through, it behaved as though it went through both. When a detector recorded which slit it used, the superposition was gone. The electron chose one path, the interference disappeared. The detector didn't physically shove the electron. It didn't bump it, or heat it, or push it aside. It entangled with the electron. It carried away information. That information leaked into the environment. Decoherence occurred. The superposition collapsed. Information, not force, not impact, not any kind of physical contact you'd recognize from everyday experience. Information is what destroys the quantum state. The universe doesn't need to push the electron into one slit. It only needs to know which slit the electron is in, and the knowing is enough. In 1999, a team in Vienna, led by Anton Zeilinger, demonstrated the same interference effect with Buckminster fullerene molecules, each one a cage of 60 carbon atoms, large enough to see in an electron microscope, objects you could, in principle, photograph. The interference pattern appeared. The molecules, objects composed of dozens of atoms, were behaving like waves, passing through both slits at once, interfering with themselves. The experiment has been repeated since with molecules of increasing size and complexity. Each time, the result is the same. The quantum behavior is there. The interference is there. The superposition is there. Until information leaks out. Until the environment finds out. Until decoherence arrives. The boundary between quantum and classical keeps receding. It isn't that large objects can't be in superposition. It's that large objects decohere too quickly for us to catch them. The environment is too noisy, too warm, too full of particles bumping against everything. The wall goes up before we can look behind it. The wall between you and that reality is made of information, and it can be removed. Now, before we go further, I want to tell you where this story is headed, because the next few chapters are going to systematically close every exit you might use to explain away what you just heard. First, Schrödinger tried to break the theory. The theory won. Then, Einstein thought he'd found a way out. He was wrong. Then 50 years of experiments proved Einstein wrong with a precision that earned a Nobel Prize. And once every comfortable explanation is gone, we'll count exactly how much the universe is hiding from you. The number is larger than you think, larger than the universe itself. Let's start with Schrödinger. In 1935, a physicist named Erwin Schrödinger sat down to write what he believed was a devastating critique. He wasn't trying to contribute to quantum mechanics. He was trying to expose what he saw as a fatal absurdity at its center. The theory said that a particle doesn't have a definite state until measured. Before measurement, it exists in a superposition of all possible states. Schrödinger found this philosophically unbearable, so he constructed a thought experiment designed to make the absurdity visible. Imagine a cat sealed inside a steel box. Inside the box, there's a tiny piece of radioactive material. If a single atom decays, it triggers a mechanism that releases a poison, and the cat dies. If no atom decays, the cat lives. Quantum mechanics says the atom is in a superposition of decayed and not decayed until something records which it is. Therefore, by the logic of the theory, the cat must be simultaneously alive and dead until someone opens the box. Schrödinger meant this as a reductio ad absurdum. He was saying to his colleagues, look at what your theory implies. A cat that is alive and dead at the same time. Surely you can see that something is broken. The physics community considered his argument carefully. They ran more experiments, they tested more predictions, and they did the one thing Schrödinger didn't expect. They kept the theory. Not because alive and dead cats made sense, because every experiment they ran, every measurement they took, every prediction they tested, confirmed that quantum mechanics was correct. The theory worked with a precision that no other theory in the history of physics had ever achieved, and the cat argument, intended as a demolition, became instead the most famous illustration of the thing it was supposed to destroy. Now we understand what's actually happening in Schrödinger's box. The cat isn't in superposition when you open the box. It isn't in superposition 1 second before you open the box. The cat is made of trillions of atoms, each one constantly interacting with the others, with the air in the box, with the photons bouncing around inside, with the walls, with everything. Decoherence destroys the cat's superposition so fast that it's essentially instantaneous. The cat becomes alive or dead long before you open the box. The environment inside the box, the air molecules, and infrared photons, and thermal vibrations, they open the box for you, at the quantum level, in a trillionth of a second. So the cat paradox is dissolved by decoherence. Schrodinger's argument fails because cats are enormous quantum systems interacting with their environment at a rate no experiment could ever outpace. The superposition is real, but it lasts for a duration so short that no instrument could ever catch it. By the time anything macroscopic could register the cat's state, decoherence has already done its work. The cat was never meaningfully in both states at once. Not because quantum mechanics doesn't apply to cats. It does. But because the environment collapses the superposition faster than the question can be asked. And this is exactly why quantum computers have to be cooled to temperatures colder than deep space. To keep the qubits in superposition long enough to compute, engineers have to isolate them from everything. Every stray photon, every vibration from a passing truck, every fluctuation in the electromagnetic field. The entire engineering challenge of quantum computing reduces to a single sentence. Keep the computation hidden from the universe long enough to get an answer. That's it. Every cryogenic system, every electromagnetic shield, every vacuum chamber, in every quantum computing laboratory on Earth exists for one purpose: to prevent the environment from looking at the qubits before the calculation is finished. Because the moment the environment looks, the superposition collapses. The computation is ruined. The answer is lost. But here's what decoherence doesn't explain. It explains why you never see the cat in superposition. It doesn't explain why one outcome occurs rather than the other. It doesn't explain what happens to the other branch, the version of events where the atom did the opposite thing and the cat's fate went the other way. Decoherence tells you the branches separate. It doesn't tell you where the other branch goes. Decoherence moved the furniture. It didn't close the door. And that question, the question of where the other branch goes, is the same question that quantum computers force us to confront. Because a quantum computer is a machine that works in the space where the branches haven't yet separated. It computes in the gap before decoherence arrives. And what it does in that gap requires resources that a single branch of reality cannot contain. So Schrödinger tried to break the theory. The theory survived. But there was still one more escape hatch, one more way to believe the world is normal underneath. And the man who offered it was the most famous physicist who ever lived. In 1935, the same year Schrödinger wrote his cat argument, Albert Einstein co-authored a paper with Boris Podolsky and Nathan Rosen that attacked quantum mechanics from a different angle. The paper described a scenario involving two particles that interact and then fly apart. Quantum mechanics says their properties are entangled. Measure the spin of one particle along a certain axis, and you instantly know the spin of the other particle along the same axis, no matter how far apart they are. Einstein found this unacceptable. He called it spooky action at a distance, and he proposed a simple, clean, satisfying explanation. The particles, he argued, must carry hidden information. When they interact, they agree on their properties in advance, like two gloves from the same pair packed into separate boxes. You open one box, find a left glove, and instantly know the other is a right glove. No mystery, no faster-than-light connection. Just information that was always there, set at the moment of interaction, carried along through space. This explanation is called local hidden variables. And it's exactly the kind of explanation that human intuition finds comfortable. Objects carry their properties with them. Measurements reveal pre-existing facts. The world is locally real. Einstein spent the last 20 years of his life believing this. He died in 1955, still certain that quantum mechanics was incomplete, that there was a deeper layer of normal, sensible, local reality underneath. He was wrong. The man who proved it was John Stuart Bell. Bell was a theoretical physicist at CERN, Irish, quiet, and deeply uncomfortable with the fact that the most successful theory in history came with no agreed-upon account of what it actually described. He thought about the EPR paper, he thought about hidden variables, and he realized something that nobody in 30 years had seen. If Einstein was right, if particles carry hidden variables that determine their measurement outcomes in advance, then those outcomes across many measurements of many entangled pairs would have to obey certain statistical limits. Here's why. Imagine two entangled particles flying apart to two distant detectors. Each detector can be set to measure spin along different angles. If hidden variables carry the information, the particles must have preset answers to every possible question packed in at the moment of interaction. But the particles can't know in advance which angle the detectors will be set to. So, their hidden variables can only provide predetermined answers to a finite set of possible measurements, and that places a mathematical bound on how strongly the two detectors' results can correlate. Bell calculated that bound precisely. He wrote it down as an inequality. If local hidden variables exist, the correlations between the two detectors must stay within that bound, always. No exceptions. Then he showed that quantum mechanics predicts correlations that exceed the bound, not by a tiny margin, significantly. The two frameworks make different numerical predictions, not different philosophical claims, different numbers, measurable numbers, numbers that a laboratory experiment could distinguish. I find this one of the most remarkable moments in the history of science. Bell had taken a question that philosophers and physicists had been arguing about for 30 years, a question everyone assumed was permanently a matter of interpretation and taste, and he had turned it into a number. Either the number falls within Bell's bound, and Einstein wins, or it exceeds Bell's bound, and local reality is ruled out. The question of whether reality is locally real had become an experiment. The first serious test came in 1972. John Clauser was a graduate student at Columbia who couldn't stop thinking about Bell's paper. His supervisors were skeptical. Bell tests weren't fashionable physics. They were too foundational, too philosophical. The consensus was that quantum mechanics worked, and the interpretation could wait. But Clauser pressed on. He found a collaborator, Stuart Friedman, and together they built an apparatus that produced pairs of entangled photons and measured their polarizations at different angles. The experiment took years to design and run. Their results, published in 1972, violated Bell's inequality. The correlations between the photons were stronger than any local hidden variable theory could explain. Einstein's picture of a locally real universe had its first experimental crack, but there were loopholes. The detectors weren't efficient enough. Maybe the photons that were missed would have behaved differently. Maybe the correlation was a statistical artifact of the detection setup. These weren't silly objections. There were real gaps in the experiment. The result was suggestive, not definitive. Alain Aspect decided to close them. Working in Paris in the early 1980s, he redesigned the experiment with one crucial improvement. He changed the measurement settings randomly during the flight of the photons, after they'd already been emitted. This was the critical step. It meant the photons couldn't have carried advanced knowledge of what was going to be measured. By switching the settings after the photons were already traveling, Aspect made the hidden variables explanation physically impossible. The photons couldn't have known. His results, published in 1982, violated Bell's inequality again, more decisively. The correlations were real. They weren't an artifact of the detectors or the setup, but there were still gaps. And so the experiments continued, decade after decade, each one closing another loophole. Better detectors, longer distances, faster switching. Each one tightening the constraints on any alternative to quantum mechanics. In 2015, Ronald Hansen and his team at Delft University of Technology ran what is now considered the first loophole-free Bell test. Let me tell you what they did, because the engineering matters. They placed two entangled electrons 1.3 kilometers apart in separate buildings on the Delft campus. Each electron was entangled with a photon, and those photons were sent to a central station where they were measured together, creating entanglement between the electrons without the electrons ever having been in the same place. Then they measured the electron spins quickly enough and far enough apart that no signal traveling at the speed of light could carry information from one measurement to the other before both were complete. The two measurements were, in the language of physics, space-like, separated, completely causally disconnected. The correlation still violated Bell's inequality to 1.3 kilometers. No shared signal possible. The major experimental loopholes were closed. In October 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to Elaine Aspect, John Clauser, and Anton Zeilinger. A member of the Nobel Committee said during the announcement that the laureate's work had shaken the very foundations of how we interpret measurements. That isn't modest language from the Nobel Committee. That's an institution with a reputation for understatement saying, in careful phrasing, that what happens when you observe a quantum system is still genuinely not understood, not a matter of missing details. A foundational open question. What has been settled is this. Local hidden variables don't exist. The particles don't carry pre-existing answers. There's no classical layer underneath the quantum behavior. The universe, at its most fundamental level, doesn't work the way Einstein hoped. The correlations between entangled particles are real, non-local, and not explained by any mechanism that involves information traveling through the space between them. The relationship is maintained without a signal. The connection exists without transmission. The comfortable explanation is gone. Every experimental exit has been closed. And if you're wondering what this has to do with the machine in Santa Barbara, the answer is everything. Because entanglement isn't just a strange property of particles. It's the primary resource that quantum computers use to do what they do. The non-local connection that Einstein found unacceptable is the engine that powers the most consequential technology of the 21st century. The universe's refusal to be locally real is what makes the machine work. In 2017, a Chinese research satellite called Mikius demonstrated that entanglement survives over a distance of 1,200 kilometers. Two ground stations, one in Dalinger and one in Lijiang, separated by the width of France and Germany combined, received entangled photons from the satellite. The correlations violated Bell's inequality by more than 11 standard deviations. The entanglement held across the curvature of the Earth, through the atmosphere, over a distance that dwarfs any laboratory. The resource that quantum computers exploit doesn't weaken with distance. It doesn't care about the space between the particles. It operates at a level where space, as we experience it, isn't the relevant variable. Anton Zeilinger, the third Nobel laureate, had gone further than Bell tests alone. His group demonstrated quantum teleportation, the transfer of a quantum state from one particle to another using entanglement as the channel, not the transfer of matter, not the transfer of a signal faster than light, the transfer of a quantum state itself, with the original state destroyed in the process to satisfy the laws of physics. Let me say what that means more carefully, because quantum teleportation is one of the most misunderstood results in modern physics. You can't measure the quantum state and send the measurement because measurement destroys the superposition. You can't copy the quantum state, because quantum mechanics forbids it. What you can do is use a pair of entangled particles as a bridge. The sender performs a joint measurement that links the original particle to their half of the entangled pair. This measurement destroys the original quantum state, but produces a classical result: 2 ordinary bits. The sender transmits those 2 bits through any ordinary channel, a phone call, a radio signal. The receiver uses those bits to perform an operation on their half of the entangled pair. And the result is that the receiver's particle now has exactly the quantum state the sender started with. The original is gone. The copy exists somewhere else. Zeilinger's group teleported a quantum state across the Danube River in 2004. They demonstrated entanglement-based quantum key distribution over 144 kilometers between 2 Canary Islands in 2007. In 2017, the Chinese satellite Mischius teleported a quantum state from a ground station in Tibet to orbit, 1,400 kilometers overhead. The entanglement holds. The distance is irrelevant. The quantum connection doesn't attenuate the way a signal fades with distance. It persists because it isn't a signal. It's a structure, which forces the question that's been building since the beginning. If the universe is hiding most of itself behind a wall of decoherence, how much is it hiding? Here's a number. Remember it, because it changes the shape of everything. Sambe. If you build a quantum computer with 300 qubits, the number of simultaneous states it can hold is 2 raised to the power of 300. That's approximately a 2 followed by 90 zeros. The total number of atoms in the observable universe is estimated at around 10 to the power of 80. Let me say that again. A 300-qubit quantum computer holds more simultaneous states than there are atoms in everything we can see, in every direction, from every point in space to the edge of the observable cosmos. This isn't a metaphor. This isn't a way of saying the number is big. This is arithmetic. You can check it yourself. 2 to the 300 is larger than 10 to the 80. The machine requires more computational states than the universe contains particles to represent them. Now, a fair objection. When Google announced Sycamore's result in 2019, IBM pushed back immediately. Their engineers argued that with the right classical algorithm and enough disk storage, Summit could perform the same calculation in 2.5 days, not 10,000 years. 2.5 days. Google acknowledged the revision. But 2.5 days versus 200 seconds is still a factor of more than 1,000. And the problem Sycamore solved was specifically designed to be easy for a quantum machine and hard for a classical one. As quantum hardware improves and the problems become more general, that factor doesn't shrink. It grows exponentially. Every additional qubit doubles the computational space. Every doubling widens the gap. The curve doesn't flatten on its own. And here's the part about the curve that deserves more attention than the specific numbers. The history of exponential technologies is a history of underestimating the back half. We're good at predicting the next doubling. We're poor at predicting what the 15th doubling looks like from the third. When that machine is in superposition, when it's isolated from the environment, when decoherence hasn't yet arrived, all of those states are active. The computation operates across all of them simultaneously. The probability amplitudes interfere with each other. Wrong paths cancel. Correct paths reinforce. The answer that emerges when you finally measure the qubits is the survivor of a process that involved more simultaneous possibilities than the physical universe can contain. So, where was the computation happening? This isn't a rhetorical question. This is a genuine, open, actively debated question in the foundations of physics. If the machine explored more paths than there are atoms in the observable universe, and the answer it returned is demonstrably correct, then something did the exploring, something performed the work. And if our universe doesn't have enough room to contain that work, then Either the work happened somewhere else, or the machine shouldn't function. The machine functions. It gives correct answers. It has been verified. It has been peer-reviewed. It has been reproduced. The part that decoherence hides from you isn't a small part. It isn't a slight correction to the classical picture. It's overwhelmingly larger than the classical picture. The visible universe, every star, every galaxy, every atom, is a thin film on the surface of a quantum reality so vast that the visible universe is a rounding error by comparison. You have been living on the rounding error. I need you to hold that, because what comes next is the mechanism, not where the computation happens, how it uses what it finds there. In 1982, Richard Feynman gave a talk at MIT that planted the seed for the entire field. Feynman wasn't a computer scientist. He was a physicist, widely considered one of the most brilliant and unconventional thinkers of the 20th century. Nobel laureate, Manhattan Project veteran, a man with an almost physical intuition for how nature works beneath the mathematics. Feynman pointed out that classical computers can't efficiently simulate quantum systems. Not because they're too slow, because the problem grows exponentially with the number of particles. Simulate 1 particle, track 2 states. 10 particles, 1,000 states. 100 particles, and the number of states exceeds the atoms in the observable universe. The structure of classical computation doesn't match the structure of quantum reality. You can't describe a symphony by reading its sheet music, 1 note at a time. His proposal was elegant. If you want to simulate quantum physics, build a machine that runs on quantum physics. Let the computer itself be quantum mechanical. And embedded in that proposal was an insight about mechanism that turned out to be the key to everything. The mechanism is called interference. Think of 2 waves on the surface of water moving toward each other. Where peak meets peak, they combine into a higher peak. Where trough meets trough, a deeper trough. Where peak meets trough, they cancel. The water goes flat. The waves destroy each other through the precise alignment of opposite phases. Quantum computers do the same thing with probability. The machine is engineered so that all the computational paths leading to wrong answers cancel each other out, like a peak meeting a trough. All the paths leading to the correct answer reinforce each other, like 2 peaks combining. The wrong answers annihilate themselves. The right answer is what survives. The machine doesn't try every possible answer and check which one is right. It doesn't search through a list. It creates conditions where wrong answers can't exist. They subtract themselves from reality through quantum interference before the calculation is finished. What arrives at the end isn't a selection. It isn't a guess. It's the last thing standing after everything incorrect has been systematically eliminated by the physics of the computation itself. I find this almost difficult to accept as a description of a machine that physically exists. It doesn't select the right answer. It creates conditions where wrong answers cannot survive. That's not a description of a calculator. That's a description of a sieve built from the wave-like structure of reality, and the material it sieves through, the space of possibilities it operates on, is the space that decoherence hides from you, the space behind the wall. And the man who predicted all of this, 40 years before the machines proved him right, was working alone, at night, in a house in Oxford he still rarely leaves. His name is David Deutsch. He doesn't fly on airplanes. He rarely leaves Oxford. He works at night, alone, in a house he's lived in for decades. He has described himself as someone who finds it easier to think about abstract structures of reality than to navigate the practical requirements of ordinary social life. He is also, by most accounts of people who work in quantum computing, one of the 2 or 3 people most responsible for the fact that the field exists at all. In 1985, Deutsch published a paper in the Proceedings of the Royal Society of London that almost nobody read at the time. The paper didn't propose a faster way to factor numbers. It didn't promise to break encryption or simulate molecules. It asked a question that sounded almost philosophical. Is there a physical machine that could, in principle, simulate any physical process in the universe? Not model it, not approximate it. Simulate it exactly, using the actual laws of physics as the operating system. His answer was precise. A classical computer can't do this. Not because it's too slow, because a classical computer operates inside a single physical reality, and that single reality doesn't contain enough resources. The computation that a quantum computer performs exceeds the capacity of the observable universe. So where does the extra computation happen? Deutsch's answer, written plainly in that 1985 paper, was that the calculations happen across multiple versions of reality simultaneously, not as a metaphor, as a physical mechanism. The quantum computer is a device that coordinates work across parallel branches of reality and returns the result to ours. The wrong computational paths cancel through interference. The right paths reinforce. The answer that arrives is what survives. The theoretical framework he was drawing on belonged to a man who never lived to see it vindicated. And to understand what drove that man to his idea, you need to understand the problem he was trying to solve. It's called the measurement problem. And it isn't a minor gap in an otherwise complete theory. It's a crack that runs through the foundation of quantum mechanics and has been there since the 1920s. Here's the problem in its most precise form. Quantum mechanics has an equation that describes how quantum systems evolve over time. The Schrödinger equation. It's smooth, continuous, deterministic, and it's been confirmed by every experiment ever performed. Feed it the state of a system right now, and it tells you with mathematical certainty what the state will be at any future moment. But here's what the Schrödinger equation doesn't do. It doesn't describe measurement. When you measure a qubit, you don't get a superposition. You get a single outcome. 0 or 1. The superposition is gone. But the Schrödinger equation, applied to the qubit and everything that interacts with it during measurement, the detector, the wire, the amplifier, the display, the physicist looking at the display, keeps running smoothly. It keeps producing a wave function that contains all possible outcomes. It never picks one. It never collapses. Let me put that more concretely. Imagine you have a qubit in a superposition of 0 and 1. You bring a detector into contact with it. The detector is itself a physical system made of atoms governed by quantum mechanics. According to the Schrödinger equation, the qubit and the detector become entangled. Now, the total system is in a superposition of two states. Qubit 0 with detector reading 0, and qubit 1 with detector reading 1. Both branches are still present in the wave function. The equation hasn't picked one. Now, the detector interacts with the wire that carries its signal, which interacts with the amplifier, which interacts with the display, which interacts with the air in the room, which interacts with the person looking at it. At every step, the Schrödinger equation just keeps entangling everything together. The wave function of the entire system, qubit plus detector plus room plus physicist, keeps expanding. It never collapses. It never picks. And yet the physicist sees one outcome. That gap between the smooth universal wave function that never picks and the definite experience of one outcome that every physicist has is the measurement problem in its most precise form. There's a separate rule, called the Born rule, that tells you the probabilities of different outcomes. It works. Every experiment confirms it. But the Born rule is an addition to the theory. It isn't derived from the Schrödinger equation. It's appended because it matches what we observe, not because we understand why it should be true. So there's a gap. The equation says superposition continues. Observation says one outcome appears. Something bridges them, and nobody knows what. Hugh Everett III, was a graduate student at Princeton in 1957 when he submitted his doctoral dissertation. His solution was radical in its simplicity. He asked, what if the equation is right? What if there is no collapse? What if every possible outcome of every quantum measurement actually happens, each one in its own branch of reality? In this picture, when you measure a qubit and see 0, there's also a branch where you see 1. Both are real. Both contain observers who see one definite outcome. The branches simply stop being able to interact with each other because they've become entangled with different environments. Decoherence doesn't destroy the other branch, it hides it. The measurement problem dissolves. There's no collapse. There's no extra rule. There's only the Schrödinger equation, running smoothly, never breaking, producing all outcomes simultaneously in an ever-expanding tree of branches. What you experience as a single definite world is one branch. The others are just as real. You can't see them for the same reason you can't see the quantum superposition of your coffee cup. Decoherence has separated you from them. Niels Bohr, the most powerful voice in physics at the time, the architect of the Copenhagen interpretation that had dominated quantum mechanics for 3 decades, dismissed the idea. He'd spent his career arguing that asking what exists between measurements is meaningless, that the wave function is a calculation tool, not a description of reality, that the question Everett was trying to answer wasn't a legitimate question. The community followed Bohr. Everett's dissertation was forced into a shorter, less ambitious form. It was published in a journal where it attracted almost no attention. He left academic physics almost immediately. He went to work for the Pentagon, not on quantum theory, on nuclear targeting strategies. He built mathematical models for how to deliver hydrogen bombs. He calculated mortality rates from radioactive fallout. He advised the Eisenhower and Kennedy administrations on weapons systems. The man who proposed that every quantum event branches reality into parallel worlds has spent his career computing how many people would die in each scenario of nuclear war. He drank heavily throughout his adult life. He smoked constantly. He told his family that he believed the many worlds interpretation was correct, and that therefore death wasn't an ending, but a branching. That some version of him would always continue in some branch of reality. He barely knew his children. He died of a heart attack in 1982 at the age of 51, on his couch, largely forgotten by the field he'd tried to contribute to. He never saw his idea rehabilitated. He never knew it would become, decades later, arguably the most conservative interpretation of quantum mechanics. The one that simply takes the mathematics at face value without adding extra postulates. His son Mark found the body. He has said publicly that it was the first time he ever touched his father. His daughter Elizabeth wrote in her diary that she wanted to die and meet her father in a parallel universe. She struggled with mental illness for years. She took her own life in 1996. A note was found saying she was going to join her father in another world. Mark became a musician. He formed a band called Eels. He has spent his career processing the experience of growing up with a man who was physically present but emotionally unreachable. A man who understood the branching structure of reality but couldn't navigate the structure of a family. I find that I can't tell this part of the story without it staying with me afterward. By Everett's own request, his body was cremated and his ashes were thrown in the trash. Because, in the many worlds interpretation, it didn't matter what happened to any particular physical configuration. Somewhere, in some branch, he's still alive. Somewhere he's watching. The technology built on his mathematics become the most consequential engineering project of the 21st century. The many worlds interpretation that Bohr dismissed in 1957 is now cited in the engineering documents of companies worth hundreds of billions of dollars. The computation that can't fit inside one universe fits, in Deutsch's view, because Everett was right. There are other branches, and Deutsch built a machine that uses them. The idea the physics establishment rejected for 30 years turned out to be, in this framework, an engineering requirement. But to understand what the machine touches when it computes, we need to understand what the universe is made of at its deepest level. And that means meeting a man who spent 60 years working his way toward a conclusion that sounds like a riddle. His name was John Archibald Wheeler. He coined the term black hole. He worked with Niels Bohr on nuclear fission. He supervised the doctoral dissertations of both Richard Feynman and Hugh Everett. He was one of the most respected and credentialed physicists of the 20th century. And late in his career, in his 70s and 80s, Wheeler arrived at a statement so compressed, it fits in 3 words. It from bit. Every physical thing, Wheeler argued, every particle, every field, every region of space-time gets its existence from information. Not information in the loose colloquial sense. Information in the strict technical sense. Binary distinctions. Yes or no answers to yes or no questions. Bits. The universe isn't made of matter that happens to carry information. The universe is made of information, and matter is what information looks like when it takes physical form. Think about that for a moment. The rock comes first, or the measurement of the rock comes first. Wheeler is saying the measurement comes first. The information is primary. The rock comes after. This sounds like philosophy until you meet Rolf Landauer. In 1961, Landauer, working at IBM Research, proposed something specific and testable. When you erase a single bit of information, when you take a system that holds a 0 or a 1 and reset it to a known state, you must release a minimum amount of heat. Not because computers are inefficient, because information erasure is physically irreversible, and irreversibility has a thermodynamic cost that can't be designed away. This is called Landauer's principle, and for 50 years it remained a theoretical prediction without direct experimental confirmation. The amount of heat released by erasing 1 bit is extraordinarily small, approximately 3 × 10 to the -21 joules at room temperature. Measuring this requires instruments of almost inconceivable precision. Then, in 2012, a team led by physicist Eric Lutz built an experiment delicate enough to measure it. They trapped a single microscopic particle, manipulated it to erase 1 bit of information, and measured the heat released. The result matched Landauer's formula to within experimental error. Information is physical. Deleting a fact about the universe releases energy into the universe. Information has weight, temperature, thermodynamic cost. It isn't a description of the physical world. It's part of the physical world. Wheeler's intuition, stated in 1990, was confirmed in a laboratory in 2012. And that changes what it means to build a quantum computer. If information is the primary substance of reality, then a device that manipulates information at the quantum level isn't modeling reality. It's operating on reality, on the actual substrate from which the physical world is assembled. Now, there's a second thread that connects to this, and it runs through the physics of black holes. I want you to follow it because it leads somewhere that I think is the strangest place in this entire story. In the 1990s, Gerard Hooft and Leonard Susskind, working independently, arrived at a conclusion that sounds like it can't be meant literally. It is meant literally. The maximum amount of information that can be contained inside any region of space isn't proportional to the volume of that region. It's proportional to the area of its surface. Think about what that means. You'd expect that doubling the volume of a box would double the information it can hold. More space, more room for stuff, more information. The holographic principle says no. The information capacity scales with the surface area, not the volume. All the information describing everything that happens inside a volume of space is encoded on the 2-dimensional boundary surrounding it. The interior isn't the primary thing. The boundary is. This wasn't derived from philosophy. It was calculated from the physics of black holes. When matter falls into a black hole, the information it carries doesn't disappear into the interior. It's encoded on the event horizon, the two-dimensional surface that marks the boundary of the black hole. Hooft and Susskind generalized this and proposed that the same principle applies to any region of space, not just black holes. Space, as we experience it, may be a kind of projection. Not an illusion, something more like a derived object, something that emerges from a more fundamental layer of information encoded elsewhere. I think that sentence is worth hearing again. Space may not be fundamental. It may emerge from information. This is called the holographic principle, and it connects directly to entanglement in a way that I think is the strangest part of this entire story. In 2013, two of the most respected theoretical physicists alive, Juan Maldacena and Leonard Susskind, proposed something that ties everything together. Their paper was titled with what looks like an equation, ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes, theoretical tunnels through spacetime. EPR refers to Einstein, Podolsky, and Rosen. Entanglement. Maldacena and Susskind proposed that these are the same thing. Let me say that again because it's easy to hear it and let it slide by. They proposed that every pair of entangled particles is connected by a microscopic wormhole in spacetime. Not metaphorically, physically. The non-local connection that Einstein called spooky isn't mysterious action at a distance. It's a geometric connection, a thread of space-time linking two points that appear separate when viewed from the surface. If ER equals EPR is correct, and it hasn't been proven, but it hasn't been refuted, and it has generated an enormous amount of productive theoretical work, then space-time geometry isn't the background stage on which quantum physics happens. Spacetime is produced by quantum physics, specifically by entanglement. More entanglement means more geometric connectivity. Less entanglement means the geometry pulls apart. Zero entanglement, and the geometric connection disappears. Space itself dissolves. Now, think about what a quantum computer does. It creates entanglement. It manipulates entanglement. It engineers complex patterns of entanglement between qubits and then uses interference to extract answers. If ER equals EPR is correct, then a quantum computer isn't just processing information. It's constructing and navigating tiny geometric structures in a space that underlies the space we observe. The computation isn't happening in a location. It's happening at the level from which locations emerge. The machine isn't operating inside reality. It's operating on reality, at the layer where reality is being assembled. And the wall is getting thinner. What comes next is the proof. In December of 2024, Google announced a processor called Willow. It had 105 qubits. Its coherence time, the window before environmental interactions destroy the quantum state, was around 100 microseconds, 5 times longer than Sycamore. In a benchmark test, Willow performed a computation that Google estimated would take the fastest classical supercomputer on Earth approximately 10 septillion years to complete. That's a 1 followed by 25 zeros, roughly 700 trillion times longer than the universe has existed. Willow completed it in about 5 minutes. But the benchmark number isn't the important part. The important part is what happened to the errors. In every engineering system you've ever encountered, adding more components means adding more potential failure points. Your car has more parts than your bicycle and breaks down in more ways. A city power grid has more failure modes than a single generator. More complexity equals more fragility. That isn't a design flaw. That's entropy. That's the second law of thermodynamics expressing itself through every piece of technology ever built. Willow broke the rule. As Google scaled up the number of qubits, from a 3x3 grid to a 5x5 to a 7x7, the error rate dropped by a factor of 2 at each step. Adding more components made the system more stable, not less. The noise didn't accumulate, the noise cancelled. I want you to sit with that, because it's the opposite of everything engineering has ever taught us. To understand why this matters, you need to know what it took to get here. Before 1995, many physicists believed that decoherence made large-scale quantum computing permanently impossible. The argument went like this: quantum states are fragile, errors accumulate, and because quantum mechanics forbids you from simply copying a qubit the way you copy classical data, a rule called the no-cloning theorem, there seemed to be no way to catch and correct errors before they destroyed the computation. Then Peter Shaw, the same man who wrote the algorithm that threatens all encryption, figured out how to protect quantum information without copying it. His key insight was to encode one logical qubit, the actual unit of information you care about, across multiple physical qubits, in a way that spreads the information through the relationships between them, rather than storing it in any single one. If one physical qubit gets disturbed, the logical information survives in the correlations between the remaining ones. Think of it this way: you can tear a page out of a book and still understand the story from the surrounding chapters. The meaning was never in one page, it was in the structure. What followed was the threshold theorem, which said that if the error rate per physical qubit falls below a certain critical value, you can make the computation as reliable as you want by adding more qubits. Below the threshold, more means better. Willow showed this wasn't just theory, it was hardware. For the first time, the machines were getting more stable as they got bigger. And the reason this connects to everything we've been discussing is this: the error correction works because the information isn't stored in any single qubit. It's stored in the relationships between them, in the correlations, in the entanglement structure. The information is distributed, non-local, and protected precisely because it has no single location that noise could reach. If that description sounds familiar, it should. It's structurally identical to how quantum computation works across parallel branches in Deutsch's framework. The information is real but non-local. The protection comes from the global structure rather than any local feature. You get the answer without being able to watch it being computed. In February 2025, Microsoft announced something even stranger: a chip called Majorana 1, which they described as the first topological qubit. The physics behind it involves exotic quasi-particles called Majorana zero modes. They're named after Ettore Majorana, an Italian physicist widely considered a prodigy even by the standards of a generation that included Enrico Fermi. In 1937, he published a paper proposing that certain quantum particles could be their own antiparticles, a property that sounds abstract until you realize it means the information they carry has no single location. Then, in March 1938, Majorana boarded a boat traveling from Palermo to Naples, was seen by other passengers, and was never seen again. No body was found. He was 31 years old. His physics survived him. His fate didn't. Majorana zero modes always come in pairs, spatially separated. The quantum information is stored not in either particle individually, but in the correlation between the two. It lives in the relationship, not in either member. This means local noise can't reach the information. A vibration here can't flip a bit that isn't here. To corrupt the information, you'd have to simultaneously disturb both modes of the pair in a correlated way, which random environmental noise essentially never does. The qubit isn't shielded from its environment, it's hidden from its environment. The protection is called topological because it depends on global geometric properties that can't be changed by local perturbations. The way you can't change the number of holes in a donut by poking it, the information is encoded in the shape, not in any particular feature of the shape. A qubit that's stable because it's nowhere in particular, information encoded in geometry rather than location, a machine that gets more reliable as it gets more complex. Each of these developments widens the crack. Each one extends the time the wall can be held open. Each one lets the machine reach further into the space that decoherence has been hiding from you. And the consequences aren't abstract. They're already being prepared for by the people who understand them best. This is the part where the philosophy lands in your lap. If you're finding this worth your time, a like or a subscribe is the best way to let me know. It really does make a difference for a channel like this. Now, back to it. Hartmut Neven, the founder of Google Quantum AI, said something after the Willow announcement that sparked a debate far larger than the benchmark number. He said that Willow's performance lends credence to the notion that quantum computation occurs across many parallel universes, in line with the idea that we live in a multiverse. The benchmark doesn't distinguish between interpretations. It doesn't prove many worlds. But when the machine does something that no classical computer could replicate across all of cosmic time, the question of where that computation is happening becomes harder to treat as merely philosophical. David Deutsch, the man who predicted all of this from a house in Oxford, has maintained a position that most physicists privately agree with, but few are willing to state as plainly. He genuinely believes that the many worlds interpretation is correct, not as a working assumption, as a description of actual reality. He believes that when a quantum computer runs, the computation happens across a vast number of parallel versions of the universe simultaneously. That those parallel instances are as real as this one, and that the machine is reaching into that parallel structure and extracting answers. He believes this the way most people believe that the chair they're sitting on is real, and the machine he helped design works. It gives correct answers. It outperforms classical computers on problems that can be independently verified. If the machine works, and the only coherent explanation for why it works requires parallel universes, what exactly is the reasonable position to hold? The question is not whether the other branches exist. The question is what it means that we built a device that uses them. In 1994, a mathematician named Peter Shor worked out something that most of his colleagues assumed was impossible. He wrote an algorithm, a set of instructions a quantum computer could follow to factor any large number into the primes that multiply together to produce it. This sounds abstract until you understand what protects the modern world. Almost all of the encryption securing the internet rests on a single assumption. Multiplying two large prime numbers together is easy. Working backward from the result to find the original primes is practically impossible. A classical computer attempting to factor a number with several hundred digits would need longer than the age of the universe. The entire architecture of digital security, your bank account, your medical records, your government's classified communications, rests on this one asymmetry. Easy in one direction, impossible in reverse. Shor's algorithm removes that asymmetry. Let me say that plainly. The lock that guards every digital secret in the world has a key. Shor showed exactly what that key looks like. The key doesn't exist yet in physical form, because no quantum computer has enough qubits to run it at the required scale. But the blueprint is published, the mathematics is known, and the machines are growing. 2 years later, in 1996, Lovegrover published a second algorithm that addresses something even more general: search. Grover's algorithm doesn't move faster through a list. It uses quantum interference to amplify the probability of the correct answer and suppress every incorrect answer simultaneously. Every wrong item cancels itself out. The right item reinforces itself. The machine doesn't search. It creates conditions in which everything that isn't the answer becomes invisible. Now, the machines don't yet exist at the scale required to break real-world encryption. Current processors have too few qubits, too high an error rate. But in 2019, Google's Sycamore had 53 qubits. In December 2024, Willow had 105, with error correction that improves as the system scales. IBM's Condor reached 1,121 qubits in 2023. The trajectory isn't linear. It isn't even cleanly exponential. It's something driven by simultaneous advances in hardware, error correction, algorithm design, and the sheer volume of investment pouring in from governments and corporations who understand what's at stake. And in 2016, the National Institute of Standards and Technology launched a competition. They invited mathematicians and cryptographers from around the world to submit new encryption algorithms, not better versions of existing ones, fundamentally different ones, built on mathematical problems that a quantum computer running Shor's algorithm couldn't break. 82 teams from 25 countries submitted proposals. The competition ran for 8 years. The final standards were published in August 2024. Think about what that sequence of events actually communicates. A government body doesn't spend 8 years and coordinate 82 international teams to solve a hypothetical problem. They don't publish binding standards for a threat that exists only in theory. The implicit message is this: the people with access to classified information about the state of quantum hardware believe the threat is real, is coming on a timeline that requires action now. But here's the part that keeps cryptographers awake. The competition was launched in 2016. The standards were published in 2024. The systems that need to use those standards, the actual infrastructure of the internet, banking, government communications, military networks, hospital databases, power grids, will take years more to retrofit. There's a window between when the quantum machines become powerful enough to break current encryption and when the new encryption is actually installed everywhere. Nobody knows exactly how wide that window is. And during that window, everything encrypted with the old standards is vulnerable. Not just future communications, past ones too. The strategy is called harvest now, decrypt later. You collect encrypted data today. You store it. You wait. The data sits on servers, on hard drives, in archives. It's encrypted. It's unreadable. It's safe by today's standards. And then, at some point in the future, when a quantum computer powerful enough to run Shor's algorithm at scale becomes available, you run the stored data through it. The encryption opens. Every email, every transaction, every classified communication, every medical record that was encrypted with algorithms Shor proved breakable 30 years ago becomes transparent. Who is collecting? Nation-states with advanced intelligence capabilities have the resources and the motivation. The infrastructure for bulk data collection exists. The legal frameworks have been debated, litigated, and in many cases, authorized. The storage is cheap. The patience is strategic. The public frontier of quantum computing is almost always behind the actual frontier. In quantum computing, where the most significant potential applications include breaking encryption and modeling systems relevant to national defense, the incentive to keep progress quiet is the highest it could be. And there's a symmetry here that deserves attention. The same physics that makes quantum computers capable of breaking classical encryption also makes a new kind of encryption physically unbreakable. In quantum mechanics, measuring a system disturbs it. You can't observe a quantum state without affecting it. Two parties sharing a secret key by sending quantum states over a fiber optic line or through a satellite link can detect any eavesdropper because the act of interception necessarily disturbs the quantum states. The eavesdropper gets nothing useful and reveals themselves in the attempt. The security rests not on computational difficulty, but on the laws of physics. No amount of computing power, quantum or otherwise, can break a system whose security is guaranteed by the fact that observation disturbs the thing being observed. China has already demonstrated this at satellite scale with Miceus, a quantum encrypted video call between Beijing and Vienna, 7,000 600 kilometers apart, protected by physics rather than mathematics. The quantum internet isn't a concept, it's being built, which means the universe handed us the lock and the skeleton key at the same time. The question is simply which one we use first. The device you're using to hear this right now is connected to a network protected by mathematics that a machine like Willow will eventually break. That isn't a theoretical statement. That's the engineering trajectory. But encryption is only the most concrete expression. Drug discovery, where molecular interactions involve quantum effects no classical computer can simulate. Material science, where electron behavior determines whether a substance superconducts or insulates. Climate modeling, where atmospheric chemistry at the molecular level exceeds classical reach. Richard Feynman's original insight from 1982 was precisely this. If you want to simulate quantum physics, build a machine that runs on quantum physics. The pharmaceutical industry has recognized this. Every major drug company now has a quantum computing research program. Each of these fields is waiting for the machine to grow powerful enough to operate within the quantum layer where their fundamental processes happen. The machine doesn't just reveal that reality has a hidden layer, it gives us tools to work within that layer. And now, I want to bring this to a close. Not by recapping what we've covered. You were here for all of it. Instead, I want to tell you the one thing I keep coming back to. There's a long tradition in the history of science of tools outrunning theories. We used fire for 300,000 years before we understood combustion. We used bridges for millennia before we could do structural engineering. We used antibiotics before we understood the immune system. In each case, the practical capability preceded the theoretical understanding, and the theoretical understanding, when it eventually arrived, was changed by the existence of the thing that shouldn't have worked but did. Quantum computers are that kind of thing. We built them. They run. They return correct answers from a space that our universe can't contain. And we don't know, not with confidence, not with consensus, not with any single framework that all physicists agree on, why they run. In 2006, a physicist at MIT named Seth Lloyd calculated the computational capacity of the observable universe. The answer? Approximately 10 to the power of 120 operations performed over the entire 8 billion year history of the cosmos. Every electron, every photon, every quark performing its quantum interactions is, in Lloyd's framework, executing a computational operation. The universe isn't like a computer. It is one. It's been running since the Big Bang, using every physical interaction as a step in a calculation whose output is the reality you're experiencing right now. Place our quantum computers inside that picture. We're building devices that operate on the same physical principles as the universe's own computation. They use the same quantum rules, the same superposition, the same entanglement, the same interference. They're not modeling the universe's computation from outside. They're participating in it, adding their operations to the total, becoming, in a small but physically real sense, part of the universe's ongoing calculation, which raises a question that I think deserves more attention than it gets. If the universe is computing something, and we add our own quantum computation to that process, do we change the output? Is the trajectory of the universe's calculation altered by what we compute inside it? We don't know. We don't know where the computation lives. We don't know what physical substrate hosts the information. We don't know whether the parallel branches are real, or whether the information layer is primary, or whether spacetime is emergent from entanglement, or whether we've built the first device that reaches past the surface of a reality whose full structure no one alive can describe. What we know is this: the universe has been hiding most of itself from you, not maliciously, structurally. Decoherence is physics, not conspiracy. The wall between you and the quantum reality underneath is built from information leaking into the environment, from the sheer thermal noise of existing in a world above absolute zero. And we found a way to hold that wall open for 100 microseconds at a time in a chamber 15 thousandths of a degree above the coldest temperature that physics allows. What we found on the other side is that what you've been experiencing as the whole of reality is the thinnest possible layer of it. The atoms of the air between you and whatever device is carrying this voice are quantum objects. Every one of them. The surface you're sitting on, the body you're breathing with, the slow rhythm of your pulse, all of it is the classical residue of a quantum process that's been running since before you were born. Your existence is a quantum computation that has been maintained by the constant interaction of your atoms with the environment around them. The only difference between you and a qubit is scale. You're too large, too warm, too entangled with everything around you to exist in a detectable superposition. The environment has resolved your quantum possibilities into classical facts long before any measurement could catch them. You are the outcome, the branch, the answer that the universe selected. But the mechanism by which that selection happened is still written in chalk on a board somewhere, unfinished. And the machines we've built are the first tools that let us ask what the rest of the board says. The machine is running right now, in the cold, in the silence, pulling answers from places we can't see. And the question that will outlast every technical detail in this story isn't about encryption or drug discovery or material science. The question is, what else has been there behind the wall all this time? And whether it noticed when we started looking